Yeah, thank you, Atul, for the introduction. So, and thanks everyone who is involved in organizing this. So today I'll talk on my recent work, which I did while I was a postdoctoral fellow at Entity Research, and this is a joint work with Thiago. He's a PhD student at Berkeley. So let me begin the talk. So in talk, I'll present in three steps. In the first step, I'll introduce and explain what the title means on split-state quantum tamper detection. And in the second step, I'll say our results in the paper and followed by few technical details. And then last 5 minutes, I'll probably introduce some open questions that one can work on after this work. So let me begin the introduction now. So let's start with the fundamental problem that we study in coding theory. In coding theory, we are interested in let's say we have message M. We want to come up with interesting codes, encoders and decoders. Essentially, both encoder and decoder are public, right? And there is some adversary in the middle. Goal is to do some bad things. One such bad thing is just observing information. We call them passive adversaries. Another dishonest behavior is like, let's say they are tampering with the ciphertext. So the problem is simple now. So we want, let's say we have initial plain text M, we encode it with the encoder, get the ciphertext, and the adversary essentially has some ways of access to it. And then you decode, and then you get some candidate M prime. And this is a fundamental problem. If you think of secure message transmission, we want M prime to be M, and which is studied by studying error correcting codes. So in error correction, our goal is that in for certain set of adversaries, we want this M prime to be M. Our goal is also like to construct these codes, interesting codes for as large adversary family as possible, right? And in error detection, our goal is again, in this case, we want to abort as long as there is an adversary in middle, right? And these are the two fundamental problems that are studied in coding theory. And now, what can we say about these problems? That both are achievable when adversary in the middle, who is dishonest, sort of is like tampering, let's say f of x and x. F is the adversary function family. And as long as f of x and x differ at constant fraction of ciphertext locations, then you can construct this, achieve this error correction and error detection. So for example, like you can have this error correcting codes like n, delta, and gamma n codes, which are possible, which are efficient. And this delta n is the plain text length. So rate of the code is like delta. And gamma n is the fraction of the ciphertext flips that codes can either correct or detect. So these codes are possible. These are studied in error correction and error detection. And one could ask, what can we achieve, let's say, for more general function family? So the function family for which we can achieve this error correction and detection are these, like, let's say, constant fraction of flips, right? And the natural question is, what can we achieve for more general adversary function families? So this is where, this other codes that I studied in my research comes into play, the so-called tamper-detecting codes and non-malleable codes. So let me introduce the security guarantee that we get from tamper-detecting codes and non-malleable codes, and then it will be more clear what I mean. Okay. So in tamper-detecting codes, the goal is again in the coding theory, uh, right? So we have the plain text M, we encode to get the ciphertext, and the adversary potentially tampers, and then you decode and you get M prime. And what we want from this M prime is the guarantee that it looks like a distribution of M prime is a convex combination of two things. In first case, it's like the original plain text M, and in the second case, we abort. So one thing to observe with the security guarantee is that is it reasonable to have such a definition? One could ask, because there is one thing, right? You cannot prevent one type of adversary, that adversary who who doesn't do anything with some probability. Let's say with P probability, adversary applies identity, and with 1 minus P probability, it applies some tampering function, right? Such an adversary can always exist in middle. So basically, it seems like this guarantee that either M or about like something that is possible, seems like, because we can at the same time we cannot like prevent an adversary who does such tampering. Like with some probability doesn't do anything, with some probability tampers with it. So tamper detecting codes essentially like puts such a restriction that this M prime in the end is convex combination of these two cases. In one case, it's like adversary has to be like an identity. In another case, it's a abort. So again, we want this PF, the probability to depend only on the adversary, essentially. Okay. So this is the guarantee that one can get from tamper detecting codes.
So for this, you need to model adversary, right?
Yeah.
So taking some function as adversary.
Yeah. So I'll come to the adversary function family. You can provide this for certain function families, and that's where adversary model will come into picture. But the goal is that this adversary function family is like more general than what you could what are studied in coding theory, like error correction and error detection.
And how do I understand tampering from errors?
Yeah, I'll come to this. I'll come to that. So this is the definition of tamper detection. And for weak tamper detecting codes, we want this M prime to be convex combination of the original message M and abort. And this probability can depend on the plain text actually. So that's why we call it weak tamper detecting codes. It's a slight sort of relaxation of tamper detecting codes. That's one reason why we call weak tamper detecting codes. And one can ask, like, where is the randomness coming? Here I'm talking of these adversaries, right? Like some distribution, right? Close in epsilon and so on. This potentially, like in classical setting, encoder can be randomized. And so randomness can come from both the encoder and the adversary, actually. Adversary could be behaving like with some probability doing some function, with some probability not doing. So randomness is over everything, adversary and the encoder decoder, and then we want to achieve this security. Okay, that's about tamper detection and weak tamper detection. And now let me.
Naresh, I got a little bit lost. I'm sorry. I think it's probably something very straightforward. So, isn't that what error correction normally also does? That either you succeed at decoding or you say, you're saying that it doesn't always detect that something has been corrupted. It might output something wrong. While here you would detect that you couldn't correct it and you would output bot. Is
Yeah,
that
yeah. Correct,
okay?
correct.
So
There
you
is
never.
the difference. There is
Go
the
ahead.
difference, clear difference. Like error correction, you always want M prime to be M. In error detection, we want M prime to be abort strictly. Okay, and in error detection, in let's say tamper detecting codes or let's say non-malleable codes, which I will introduce later, decoder need not know that adversary detected or adversary changed something. The only thing, like if you look at non-malleable codes, is that for every message M, we want this final candidate M prime is a convex combination of two things. After decoder applies. So essentially, we want to be, in one case, this has to be M, and in other case, it's some distribution dependent only on the adversary. So if you look at the detection and non-malleability, right? So detector basically the decoder need not know whether it's, let's say, M or some other thing. The goal is like to show this M prime is convex combination of two things.
I see. And why don't people consider because intuitively it looks like the thing that may be more relevant is when the decoder also knows whether it succeeded at decoding or whether, I don't know,
Yeah.
some tampering was detected.
Yeah, I guess
Is
like
that too
in some
difficult?
applications, there are some applications of this non-malleable codes in distributed storage and so on. So for those applications, basically, if you use non-malleable codes, basically prevent some black box. Like if you are given black box access to this encoding and decoding things, then still they cannot gain using those things, they cannot basically it prevents from using such black box attacks. So basically, you can think of M as like your secret key, and you encode it and store the ciphertext in some, let's say, like two ciphertext. And if adversary tampers with the ciphertext in the hope that when he decodes, he gets some M prime, right? So he will not get the actual secret key. So in that sense, these non-malleable codes play a role in preventing black box attacks. So that's one reason why they were studied in past in classical literature, but they have also found applications of non-malleable code set in various other settings like non-malleable commitments, which play roles in achieving secure multi-party computation against active adversaries. So even though they were introduced to study basically potentially like negate adversaries with black box access, but yeah, they have been found to have. But one thing that we gain from studying this thing is this adversary functions can be now more general.
Okay. So there is a correctness condition, right? It's not security condition.
Yeah, this is if I show this M prime is this convex combination, then I've shown non-malleable code security.
So how is this security? You're proving it against some
family.
So you were just saying that you got some M prime of the M. So how do I know that it's secure? What is the definition of security?
This is the definition of non-malleable code. The definition of non-malleable code is we'll say certain encoding and decoding to be non-malleable code for adversary function family F, when if one can show that M prime after decoding is convex combination like this. That's the definition of non-malleable.
Adversary, for any adversary, if I have two encodings, the decoding should be. So I want like distinguishability game and the security game. So how do I found that?
Okay, okay, let me come to the adversary model a little bit more clear. After that, if you still have question, I can answer. Okay, so in some sense, like you can think of non-malleable codes as relaxations of error detecting codes. In error detecting codes, we always want to abort, but in non-malleable codes and tamper-detecting codes, it can be convex combination, right? And
sorry, Naresh, could you explain the connection with malleability? Because malleability is normally that you combine two code words in some way and it gives you a new code word, which I guess should not be possible here. Could you explain what the connection is given the formal definition?
Yeah, the non-malleable attacks are the following. You are given encoding of, let's say, 0, right? And we'll say it's malleable if you can convert encoding of 0 to a encoding of, let's say, different message, encoding of 1, right? If you can do such an attack in middle, right? For that adversary, basically encoding of 0, now encoding of 0 became encoding of 1. Now when you decode, you will see 1, right? So basically that you can, so basically the ciphertext is malleable. We'll say that. But if you use non-malleable codes for this adversary family for which I can give this non-malleable code security, such an attack is not possible. You cannot like change encoding of 0 to encoding of 1.
Yeah, and it's not obvious from the definition, right? It's just a definition. You need to prove these things.
Yeah, like you look at this definition, right? Like for adversary in the middle F, this M prime will look like this, right? Like if this should happen for every M. So for, let's say, if M was 0, you should have this M prime should be like with some probability 0 and rest of probability some arbitrary distribution. If M was 1, it should be with the same probability, it should be 1, and 1 minus P probability, it should be some arbitrary distribution. So this security is giving that preventing malleable attacks.
Sorry, one
convex combination of two different things can be the same thing, right?
Sorry?
The convex combination of 0 is something made up. Can be same with convex combination of 1 with something else. Yeah.
See, this PF should be same for every function, for every M. That's why this security is for every M, PF should be the same.
Yeah, it doesn't depend on M.
Yeah, that's very crucial. That PF and df should not depend on m.
Okay.
And M I should think of as the encoding of the message itself, or M is the message itself?
M is the plain text message M. So
That's
let's
a bit
go.
odd.
M is the plain text M. You encode, you get some ciphertext C. It was tampered, and then you decode to get M prime.
Oh, I see.
And
I see.
we want, okay,
Got it.
we want
Yeah,
this.
so M prime is encoding of M, decoding of M, and the thing in between,
Yes,
and
yes.
then you're saying this with okay, right. And sorry,
Okay.
one last question, if I may. So non-malleable codes and the tamper detection code. So what is the difference between them? Is it just
The
that you
only
have DF
difference,
instead of identity? Is that
yeah, correct. The only
Yes.
difference between non-malleable code and tamper-detecting codes is the following. You can think of tamper-detecting code is a strengthening of non-malleable code. In non-malleable code, there is this DF is a distribution over plain text message space. In tamper-detecting codes, we want this DF to be strictly abort, like one fixed symbol.
No, I mean, DF can come, right? And say M belongs to 0 and 1.
Sorry?
Say M belongs to 0 and 1. The message space is 0 and 1.
Okay.
And then PF is half.
Message space is 0 and 1. Okay. Then you want to say this M prime is with half probability 0 plus with 1 minus basically another half probability. What do you want? What is this DF?
That will 1, right?
Okay, you can keep it 1. Then what will happen? This M prime distribution in one case, it's like fixed.
It comes to be the same, right? For 0 and 1. Okay. So by the way, DF is distribution, it's not a single number, right?
Yeah, DF is a distribution that should depend only on the adversary function. I mean, you can try all the attacks. I'm sure I can give you like just a like it would be a simple. I guess like we have to work on both, but we should be able to. Okay. So let's move on. Like this is a security guarantee that these non-malleable codes and tamper-detecting codes provide. And what do we gain out of these things that basically like can we construct? So the next question is, can we construct these non-malleable codes and tamper-detecting codes for general adversary models? That by general adversary models, I mean that our function here, tampering ciphertext, is like n bits to n bits. Like adversary could be anything in between. Then can I provide such a security? And for that, the answer is that it's a no, because I can always come up with an F here in middle, which is essentially you first decode, add 1 to it, and then you encode. And that you can think of that as the function in middle. And for that function, you always get M prime to be M plus 1. And you cannot write M plus 1 as a convex combination of M and arbitrary distribution for every M. So basically, like you cannot provide either non-malleable code or tamper-detecting code security when adversary function family is general as possible, right? So the question is like, okay, so error correction is not possible, detection not possible, even these non-malleable codes and tamper-detecting codes are not possible for generally adversary models. And the next natural question is, for what models can we study these codes? And one model that is studied.
No, sorry. Before you go on, in the previous thing, you said F is this function that you've written, but the adversary doesn't have access to the decryption function, right?
No, that's why I said in the beginning itself, this encoding and decoding are public. The randomness that is used in the encoding need not be public. It could have this own randomness. You can have encoding and decoding strategies are public.
No, but like, for example, if you do secret key encryption, right, the algorithms are public, but the decryption also uses the same randomness, for instance, right? So here you're not accounting for that. That's why I was a little bit curious.
Yeah, so we don't have the randomness. This encoder is potentially random, can have internal randomness, and
But the
decoder
decryption
can.
is the decoder is deterministic, is it?
Yes. So there is no secret key here, like between encoder and decoder.
I see.
Still, we can achieve this security, huh?
So therefore we cannot, right? You're saying that in the general you cannot. Okay, but if there was, then this doesn't apply.
If there was,
specific attack doesn't apply. I don't know if other attacks apply. But,
right. Yeah, don't know. Like I guess there is non-malleable codes are also studied when there was secret key. Yeah.
Okay.
I guess. Yeah.
So Satul is saying if you encode with secret key, then your argument will fail because the adversary will not have the randomness that is there.
Yeah, the decoder uses. So yeah, for this F, he can fix encoding with a particular randomness, like any randomness that works. That makes this entire F a deterministic function because decryption is deterministic and encoder for a fixed randomness is deterministic. So F is deterministic. And from the correctness of the codes, you want the correctness when F is identity, M prime should be M always. So basically, for this F, you cannot achieve non-malleable codes for tamper-detecting. Okay. Any more questions? Okay. So yeah. So that led to ask a question that okay, under what adversary models can we at least think of providing tamper detection and non-malleable code security? And one model that is adversary model that is studied in the literature is the so-called split-state adversary model. And the split-state adversary model is named naturally that your ciphertext is like concatenation of X and Y, but you allow adversary to be coming as a function of F tensor G. So F acts on tampers X to X prime, G tampers Y to Y prime. And this F can be any arbitrary function tampering X to X prime. G can be any arbitrary function tampering Y to Y prime.
Splitting can also be arbitrary?
Yeah, like can be arbitrary, but typically they are studied when they both are equivalent, but you can also study that. Okay, so let's just stick to equal splits for now. And yeah, this is the split state model. So one can ask the natural question in the class quantum setting. We can study this.
No, sorry, I have a small question about the previous slide. So here you're saying that for all, so suppose I have n bits and I split them, X is the first n by 2 bits and Y is the next n by 2 bits. So certainly we want security against that. But does it mean we require security against all possible permutations in the sense that any n by 2 bits and any n by 2 bits, or is it that you have to like fix the order a priori and then you require security only against those?
Yeah, typically study is the first half is called X, second half is Y.
Okay. So you just fix the bits in a priori and then require the adversary. Okay,
Yes.
Got it. Thanks.
Right. And this is studied in the classical setting over the last few years. And now in my research, I studied everything, the split state model in the quantum setting. So
sorry, what is the motivation for this model? I mean, I understand that we cannot do the most general thing, but then why is this the right model to consider?
Yeah, people also have studied when adversary function families, let's say polynomial sized adversaries and so on. But the motivation comes in, let's say, this split state model naturally has applications to secret sharing and so on because of the split part here. And it's also
has applications to what? Sorry, I didn't catch that.
In secret sharing, non-malleable secret sharing, and
I see. Okay.
And they will also have applications in like commitments. Commitments could be in So another thing which I think is also, let's say you encode, you can think of the ciphertext split naturally in the following sense that first half you sort of like send through one channel and second half you sort of send through second channel. You could say something like that, or you could also, in fact, another thing in distributed database settings, storage setting is that the ciphertext, you store X on first server and Y on second server, which is that, let's say one is in Singapore, another is in New York, something like that. So then the split thing is natural, right?
Right. Okay, thanks.
And what kind of results do we have here in this model?
We can achieve non-malleable codes and tamper-detecting codes in the quantum setting.
With arbitrary FMG.
Yeah, I'll come to the results. Okay, so right. So
Hello.
the first adversary model that we study is the fixed state adversary model with local operations. So these local operations make sense when, let's say, message M is quantum, then X and Y is quantum register, right? And then you want to study tampering functions, let's say tampering CPTP maps, like U takes X to X prime, Y to Y prime, and so on. So this is a fairly natural local operations model. And we can also study something a bit more stronger, which is local operations and classical communications model, where M is quantum, X and Y are quantum, and this in between, this is classical information. So adversary can tamper, send some classical information based on that they tamper and so on, like back and forth. And then you get finally X prime and Y prime and so on. And this in LOCC model, this communication can be arbitrary. There is no restriction on the communication. And this is the second adversary model that potentially one can study in the quantum setting. And the third model is the split state adversary model with entanglement, which was studied in Boddu, Goyal, Jain, Rabiro in 24, where in this setting, we have message M and the ciphertext XY, and adversary is allowed to use some entanglement to tamper X to X prime and Y to Y prime. The reason why this makes it more interesting is that the correlations that you can induce over these registers X prime, Y prime using quantum entanglement is potentially stronger than, let's say, when you don't have entanglement. So that's why studying this model is more natural in the quantum setting with entanglement, right? And
so here there's no classical communication, is it?
Yeah, there is
It's
no classical communication. Yeah.
Okay.
And so quantum states, like even if they were pure in the beginning and doing it this way, they become mixed at some point, right?
Yeah.
X and X prime and Y prime are mixed here at least.
Yeah. To begin with, X and Y can also be mixed.
X and Y, yeah. So, and you study only unitary tampering because you could have like channels there as well, right?
Yeah, like because we study in the, let's say, depends on, like, let's say if I have like tamper, like the CPTP map, I could also have a different adversary who does like Steinspring isometry.
Yeah.
So and basically that the ancilla that you need can be borrowed, they can be get zeros, right? Yeah. And then that side information can be put in W1. So basically, like you can at least in the entanglement model, you can, without loss of generality, you can study just unitaries in middle. But anyway, you can study CPTP maps.
So here you can apply any local operation.
Yeah, any local operation that takes X and W1 to X prime and W and so on. Okay, so this is the quantum state adversary model with entanglement. So now at least this is what in the title, on quantum state tamper detection we mean. So basically we study tamper detection in these quantum adversary models that I have introduced.
So can I think of these models as you are putting some structure on the adversary which is plates and bounded, right? So you, instead of general function F, you have functions decomposed into two parts,
right.
F and B. Where F and G are arbitrary. Still the overall thing may not be, is not an arbitrary function, right?
Yeah.
So,
yeah. I mean, that's the restriction on the adversary.
Well, like U and V are separate. Adversary attacking is separate, but joints and joint delimitated control. Right. So the idea is more apparent because you are using local operations instead you could have had global operations. So for global operation, you know that there is no security because it's so in classical case. There is no security. But why we that's important to security? So I don't
Okay. Let's see what is possible in the quantum setting. So first, let's see whether you can have tamper detection with classical codes before getting into quantum codes. In classical codes, basically, like it's simple thought that it's impossible because of the substitution attack. The attack is simple.
Sorry, so before you go, so
Yeah.
it looks like for arbitrary function you couldn't prove security, and for this kind of cases you could prove security. So are there like other kind of special functions for which you can have security?
Yeah, like there are some works which studied when adversary function families like decision trees of certain depth or poly-size circuits, or I mean, the various things are considered. Three-state model is also one thing
So
that
that
is.
is one example where
So, like, let's come to this security of tamper detection with classical codes, and that is impossible with classical codes because of the substitution attack. The attack is simple, that since encoding and decoding are public, so adversary F and G could be the following. F is like you first encode to a particular fixed random. Let's say R is like all zero string. So encoding is a function, and F outputs the first half of it, X prime, and G outputs the second half of it. So essentially that F and G can be defined like that. And for such an adversary, that is a clearly a fixed state adversary. And for such an adversary, basically XY is basically modified to X prime and Y prime, such that X prime and Y prime is an encoding of zero. So for such an adversary, right, like decoder will always output zero because it's an encoding, this X prime Y prime is an encoding of zero, valid encoding.
assuming that it knows the random.
Right. That's why I fixed. And here I'm crucially using that this encoding and decoding are correct with probability 1. You can, of course, like also extend, let's say when the probability is like negligible, some argument can be done, but I'm using that fact that correctness with probability 1, and that's why I could fix any randomness. Like and that's why I fixed all zero string to give you split state adversary, right? And for such an adversary, decoder always outputs zero, right? And it means that you can at least not achieve tamper detection with classical codes, right? Because I'm giving you a split state adversary who always outputs zero for any encoding, right? So this means that tamper detection is not possible with classical code. So what can we do with quantum codes, right? Yeah.
So what do you mean by fixed randomness of the example you took zero,
Right.
all zeros, etc. But in the setting, so we assume that the adversary has access to the same randomness with the encoder used. Is that what you mean?
No. Encoding, the process of encoding and decoding is public. So I know when you have a random function, right? When you fix the randomness that you are going to use for the random function, it's a deterministic function.
Okay, we use the same seed and seed is
Yeah.
released.
Yeah. So yeah, I need to give functions, right? So that's for that I fix the randomness essentially.
Yeah.
And now let's come to tamper detection with quantum codes. Again, let's say if you have unbounded entanglement, one can do the substitution attack. So because of course I can always take the unbounded entanglement to be an encoding, valid encoding of some message, and then just substitute, replace, right? Such an attack can be done if you are allowed to give unbounded entanglement. And the natural question that we ask is what happens when listed adversary shapes bounded entanglement, right? Bounded entanglement in the sense that if your ciphertext length is like n bits, n qubits, let's say we give some fraction of entanglement is allowed. Okay. And then
In first case, I'm not like I don't didn't memorize that definition security. So how does the substitution attack work?
Okay. It works in the classical case also. This M prime is always zero for a listed adversary. So, but for tamper detection, I want this zero to be convex combination of some message and abort, right? For every M. That is not true when your M prime is always zero, right? So
how it happens in unbounded entanglement?
unbounded entanglement case also M prime is always zero. Because if you share encoding of zero as the entanglement, and then let's say I change the first bit with the entanglement that I shared, just replace attack. So, and when I decode, I'll get 0 back.
Basically, I can transport, teleport any bit at the other part.
We are not teleporting, we are just like shuffling registers. Like shuffling, what I mean is replacing. Like if someone gives me 2 registers, I just have to replace like that.
So entanglement?
Yeah, entanglement is unbounded. Entanglement is used to share a valid encoding of a fixed message. In this case, I'm taking 0. Encoding of 0 as the shared entanglement.
Yeah,
Okay, I guess like when the picture comes, I can it will be more clear. Let's go back to the picture. I think yeah. Suppose here this W1 W2 is an encoding of 0, right? And then I just W1 I makes it as X prime because I can do any operation here, right? Q. Here V W2 is given as Y prime, right? Then this is W1 W2, right? For that an adversary, and then you get W1 W2 is like an encoding of 0, so N prime will be 0.
Yeah, I think it can be a good correlation.
And is it the same? Like, is it the same argument with randomness? Does the adversary also have the same fixed randomness? Or here also? Or here is the encryption deterministic. Is it different?
Yeah, the decryption is not deterministic in the quantum case, right? It's a quantum operation. But I didn't get your question. Can you?
So, how will the adversary have the shared entanglement state in encoded instead of 0? Is my question.
Okay. Because of the flexibility of the model. So model is allowing you to okay, this model is allowing you to share any. This is the adversary is given by tampering U and V operators and the state side. Adversary is allowed to take any side.
Yes. Okay. Okay. They are
So then adversary has flexibility in the model. Okay. So this means so anyway, this is the question that we studied broadly, that this tamper-detection codes with bounded entanglement. And what applications do we have such quantum tamper-detecting codes, even if we construct, right? And these are the 2 questions that we answered. And let me get to the results and some technical details. So before saying results in the quantum setting, so here I've only mentioned the definition of non-malleable codes and tamper-detecting codes in the classical setting till now in the introduction. So the security of non-malleable codes and tamper-detecting can be fairly generalized to the quantum setting in the following way. For non-malleable codes, in the work of BGJR, this is the formal way, that what I want of non-malleable codes is like convex combination of 2 things, right? In the classical setting, in one case, it should be the same as M. In another case, like some distribution independent. So for the quantum case, it becomes it's natural to consider. Let's say you can also have mixed states and so on to begin with for M, and M hat you can think of as like external correlations of this M. And now you go through this, you have encoding, tampering process, and then decoding. And this final state, eta, M hat state, in one case, it's just the original sigma M hat along with correlations. And in the second case, the correlations are broken and replaced. This M register is replaced with a state that depends only on adversary. Okay, this is a strength. You can say it's a natural extension to quantum messages. And for tamper detecting codes, we want that M hat looks like eta M hat looks like the same, except that in the second case we want it to be about in the register M. Okay, and this is the definition that we get that we consider in this work.
Might be a silly question, but how does my abort register look like in quantum? Is it?
You can think of like in a this register M might have like working in the Hilbert space of like 2 power n. You can think of all zero string as like about like it's a symbol.
Okay, it's this one.
It's a synonym that you always output for something. Right. So our first result is that at least in the quantum setting, the quantum non-malleable codes in the T-split local operations model implies quantum tamper-detecting codes in the T+1 split local operations model. So this is a significant departure already from the classical setting, because in classical setting, we cannot have tamper-detecting codes, which is what we proved, impossibility result. But in the quantum, using quantum codes, basically you are giving something more power to the encoder and decoder, right? And then it seems like non-malleable codes already imply tamper-detecting codes in extra split, okay? And we use that to show that basically there exists a constant rate quantum tamper-detecting codes in the three-split local operations model. The way we do is by first constructing quantum non-malleable codes in two-split local operations model, constant rate, so that this basically this lemma implies for three-split tamper-detecting codes. Okay, and right.
Sorry, no, it didn't follow. So you're saying you showed that there exist tamper detection codes for the two-split model, and then you use the lemma to show it for the three-split model. Is that what you said?
Yes, but we can show quantum non-malleable codes in the two-split local operations model. Like I have given like three models, right? Local operations, LOCC, and with the entanglement. In the local operations model, we construct non-malleable codes in two-split model, quantum. And that implies quantum tamper-detecting codes in three-split local operations model.
Right. Sorry. Okay. Sorry. Thank you.
So, yeah, in the classical setting, we do know concentrate non-malleable codes in two-split model, but we extend those things for in the local operations for quantum messages as well. And but the techniques that go into such constructions are fairly standard. So maybe I'll not get into that. I'll get into the like this how non-malleability implies tamper detection in the local operations model.
Okay, and just to be sure that the tamper detection is strictly, well, not strictly, but it is, well, okay, it is stronger than non-malleable codes, right? The definition is stronger. Is it known to be strictly stronger in general, or
because
it is just that we don't know the, like, is there like an example?
It is strictly stronger in the following sense. In the for classical messages, classical adversaries in the two-split setting, non-malleability is possible, but tamper detection is not possible.
Okay.
So,
thanks.
Okay, so that's why I said this is already a departure using quantum codes from classical setting, because in classical setting, tamper detection is not possible, but using quantum information, tamper detection is possible, at least in the local operations model.
Okay, and sorry, one last question before, I'm sorry, I know I'm interrupting, but just to quickly check. So T-split is, I think all the splits you said were equally spaced, right? The number of bits were. So when you go from T-split to T+1 split, is it really crucial that we have all n bits, or maybe it's just enough to have one more bit? Like, like if T is, say, n bits, then the total number of bits being used in the first one is Tn bits, right? And I guess you would use Tn bits plus n bits. So I was wondering if the plus n is actually needed. Is it, or maybe you just need like Tn plus 1 qubit or something along those lines. Is it clear?
Some depending on the epsilon that you want to achieve. Basically, like if you want like exponentially tiny epsilon, then you need like a delta n or something like that. That Tn plus delta n, something like that.
Makes sense. Okay, thank you.
And right, so let's try to understand. I mean, if there is something that you want to take, I guess that statement that non-malleability implies tamper detection in this in the local operations model. First, let's understand the definition of non-malleability in the quantum setting. The definition was this, that the final state after tampering process, encoding, tampering, and decoding is this final state. It's a it should be in two cases. In the first case, it's like adversary is like the overall process is like an identity map. M hat comes as is. In the second process, it's a decoupling map. Basically, like the M hat register comes as is, sigma M hat. And this M is like decoupled, the correlations are decoupled and replaced with an arbitrary state. Gamma MA depends only on the adversary. So these are the two cases, the security guarantee that you get from a non-malleable code, quantum non-malleable code, right? So our idea is simple, that you see, we are only in these two cases, right? In one case, it's an identity map. In second case, it's a decoupling map. So suppose if I could send, let's say, one half of EPR pair, let's say one EPR pair, and feed in, right? And second half I'll keep in a separately. In the first case, this E comes as is, the first half of EPR, and correlations intact. And in the second case, that E decouples from the basically the purification of this E hat register. So in one case, EPR comes as is. In another case, EPR state decouples. And we know in the quantum case, we don't have to work only in computational basis. And there is a test that you can do, which is Bell basis test, that differentiates between these two cases. Basically, if EPR state comes, it accepts. Anything like decoupled state comes, it rejects with high probability. So basically, this is the overall idea that when put into work, you will get the T split to T plus 1 split construction. So more formally, that let's say I want to achieve the tamper detection for message M. What I'll do is first prepare EPR states E hat, and I will use T splits to protect M along with the first half of EPR states E. And in the T plus 1 split, I'll put the second copy, like E hat register of E, right? And in the first case, from quantum non-malleability definition, this E hat comes as is, like EPR state, right? When T split adversary does not tamper, then E hat comes as is. And if T plus 1 adversary tampers E hat, that can be detected via Bell basis measurement. It's crucial that because when you consider an EPR state and you do operations only on one part of it, that is the T plus 1 split adversary, that can be detected by Bell basis measurement, right? And that is used. And in the second case, E hat comes as in decoupled, right? In a decoupled setting, the Bell basis measurement already rejects with high probability, right? So in both the cases, non-malleability, like in one case, if T plus 1 adversary does not do anything, then we accept. Otherwise, you reject. Okay. In the second case, right, you reject always. So basically, you are always in these two cases. You either output the same original message or you reject. So that's why non-malleability implies tamper detection in the local operations model. Is this clear? The argument?
Let's go back.
Yeah. This one?
So M and N registers E cap.
Yeah. No. Like M is the message for which I want to achieve tamper detection. So as part of encoding, I prepared this registers E hat. Like EPR state can be efficiently prepared.
Okay.
So E hat. Yeah. And I'll use quantum non-malleable code to protect first M and E together.
Okay.
Okay. And E hat register I'll put in a T plus 1 split. Okay. That's why I use T splits for non-malleable code and T plus 1 split for storing second half of EPR state E hat. Okay. And then you can consider the analysis in the two settings. Local operations, right? Like T plus 1 can be analyzed. First, you analyze T splits, followed by the T plus 1 split. So that we can do in the local operations because they are commuting, right? T and T plus 1. So that's why we can analyze the T split adversary first. That if T split adversary does not tamper, right, then non-malleability implies E hat are EPR states. And T-split adversary tampers, then E hat comes like as a decoupler, right? So basically this T-split adversary, two cases I have considered. Now in the first case, when E hat are EPR states, now when T+1 split adversary tampering E hat can be detected via bell basis measurement. Okay, that you know, right? Like when you have an EPR state, or operation only on one part of it, like basically any Fourier operation takes it to an orthogonal state. So basically that's why bell basis measurement will detect. Okay, and that the first case is analyzed because then you either output an EPR state or abort, right? And in the second case, when E and E hat are decoupled, then bell basis measurement rejects with high probability. Okay.
So any correlation that allows for detection of these two states would be good enough, or this is into.
Yeah.
And you are telling that for bell basis, it rejects with high probability and probability.
Yeah.
So from here, I cannot say that the one how many whatever the number of BPF pairs you use, we cannot say that this is the one needed to achieve tampering detection from normal usage. I cannot quantify the amount of entanglement that allows me to achieve tamper detection from normal usage.
Yeah, like basically, if you use n EPR pairs, then you achieve like 2 power some constant times and security guarantee. So I mean that's why I said the T+1 split number of EPR pairs that you are using, like this test that needs this E hat this product test, right? So I mean that comes into play there. You can also use one EPR pair also, but the security will be tiny.
I think how will you distinguish the two cases for determine the
yeah. And the crucial property we are using, we are giving some power to decoder that jointly doing something, right? Which adversaries are not, doesn't have in the model, right? But that is not something like, so something that you are giving only for quantum non-malleable codes or quantum tampered. That was true for classical codes as well. The decoder is allowed to see the two splits together, right? That was there for in general for non-malleability and tamper-detection. Just that in quantum case we have additional, we don't have to restrict to computational basis. So we are using the bell basis to differentiate this product. Okay, so this is
also from here I cannot see that I cannot say that if I had classical correlation, so instead of having EPR pair, you have something where it's less correlated. It's not guaranteed from this analysis that it will be helpless.
Yeah, like if you have classical correlation, this first case itself won't go through, right? That when E hat our EPR or like classical correlations doing something on this, like you cannot like that only bell basis has that property. Like if you have like maximal correlations and doing one takes it to orthogonal. That's, yeah, like so anyway, like the crucial thing is why is it possible is because of the bell basis test. That will. Okay, and more formally in pictures is this, you know, the T+1 split, the M and E are used to non-malleable code. You get the T splits and then you analyze it like that, like E prime. Yeah, so analysis is the same thing put in picture. Okay, and now what is known prior to our work is this in the when there is no entanglement, which is local operations model, is that the Bergamashi's work in 24 constructed for quantum messages, but in weaker model, that n split model. Let's say if your ciphertext is like n qubits, then each qubit is allowed to be tampered locally, like by a arbitrary map, but they have to be done like n splits. Each split is 1 qubit. But we do when n is like 3, like n is split into n by 3, n by 3, n by 3, like that. Okay, so that's the strengthening from the earlier work. And so the next question that we answered in this work is that what can we do? We know that we cannot achieve tamper detection when there is an unbounded entanglement. So with bounded entanglement, what can we do? And we also construct concentrate three-split quantum tamper detecting codes with bounded entanglement. Let's say if your n is the ciphertext length, the total ciphertext length, then as long as the bounded entanglement size is like some n by 20, some fixed constant that we give, then we know how to construct quantum tamper detecting codes. One fairly natural way to do is that, let's say I first construct non-malleable codes in 2-split and then somehow extend it into 3-split, right? And so what the argument that I said for local operations will also go through for bounded entanglement case, as long as I have some strengthening of this non-malleable code property called augmented property. Okay, augmented property, I guess people who are familiar in the non-malleable literature will know, but you think of it as like external thing that you need to let the arguments go through. So if we take this path, then what we mean is that we need this 2-split quantum non-malleable codes with entanglement. And that is an open problem. So we don't know how to construct constant rate 2-split quantum non-malleable codes with entanglement. Even now it's an open problem. We know how to construct up to inverse polynomial rate, but we don't know how to construct constant rate. And constant rate is what basically, people are more interested in. And so we follow the following strategy, that we first use 3-split quantum non-malleable codes, which we know from earlier work. And we use our reduction to show 4-split quantum tamper-detecting code with bounded entanglement. And what we do is, this 4-split, the argument is the following, that you can think of like X, Y, E, Z in the picture as like 4-split ones, and we say that even if you combine 2 splits, we still argue tamper detection property in the entire process. And to do this argument, it's non-trivial, but I'll tell one thing additional that you need over the earlier works. Basically, you need the decoupling idea that I mentioned. EPR states like you use somehow non-malleable codes to get into these two cases. EPR comes as is and decoupled in the second case, and some 2 design unitary properties to argue as 3-split. And let me say one crucial property that we use in all of constructions of 2 design unitaries. Okay, so this is the following property that we use crucially, that 2 design property, which is called poly-dwelling. So poly-dwelling means that you will use some set of unitaries which are like subgroup of Clifford group, such that, let's say, if you apply on any fixed Pauli operator P, then it randomizes that Pauli P to Q. So this happens for any fixed P. Q is random. So as long as C is randomly picked. So essentially what it means is that as long as, let's say, you think of P as adversary operation, some Pauli operation, like it could be Z gate also, P is gate and so on. So, and C as your encoding, okay? And you encode first and then you apply with an adversary function P, and then you undo by decoding. Then it's like applying a random Q, right? What does random Pauli operator does to a plain text? It decouples, right? So basically in that way, this 2 design unitary property, that a random Clifford, random 2 design unitary on any fixed Pauli gives you a random Pauli matrix, non-identity Pauli matrix. Okay, so this is a crucial property that is used in all our arguments. Yeah.
In the last slide, could you go back one slide?
Yeah.
Yeah. This is what you showed.
Yeah. So what I was saying is that this 4-split construction comes as a from T to T plus 1, but then we also combine 2 splits and still argue that 4-split is also 3-split tamper detection code. And I was saying the crucial, the argument is very elaborate. The crucial thing that one needs is that two design unitary property, which I thought is okay. And that's about the one. And let's note down the properties that we have of our 3-split quantum tamper detecting code, that we are able to provide security guarantee for when the adversary shared entanglement size infinity, like unbounded, and we need the adversary requirement on the shared entanglement only on one split actually, and which we will exploit when we give applications in tamper detecting secret sharing. And this is optimal up to constant factors because substitution attack will apply otherwise. And we also have this additional property of our tamper detecting code that it is a 3 out of 3 secret sharing scheme. And basically, this means that this is again a crucial departure from classical information setting because we know classical non-malleable codes which are not secret sharing. Okay, so yeah. And now let's come to the applications. Like let's say we have 3-split tamper detecting codes now in bounded entanglement with under bounded entangled adversaries, and we want to construct some interesting primitive which is also this tamper detecting secret sharing. This is again fairly natural, like extension of secret sharing additional property which is tamper detection. Like as long as there is an adversary in middle tampering, when you reconstruct the secret, you abort. Like basically it's tamper detection. When there is no adversary in middle, then you get the same M as is. Okay, and this is the definition basically that you need. I just here put the detected thing because there is an adversary in middle. But the more naturally the security is that this MM prime is a convex combination of two things. In one case it's M, and in another case it's an abort. Okay, this is the same, the natural extension of tamper detection to secret sharing. And this is impossible to achieve using classical codes because of the same substitution attack. And but we construct basically tamper detection in secret sharing using this our tamper detecting code as core component. And we additionally need classical secret sharing scheme, which has resilience against certain quantum leakage. Right. So how do we go about doing that? That there is an established application. Let's say if you have 2-split non-malleable code, then there is a compiler that is used in the earlier works to construct threshold non-malleable secret sharing. And in this work, we come up with a compiler which is inspired but different compiler to compile 3-split quantum tamper detecting code to a threshold tamper detecting secret sharing scheme with some star. I'll say what that star is later. And so essentially the idea is somehow we will, I'll say the crucial idea later. So let me talk. So this is a candidate threshold tamper detecting secret sharing scheme one can come up with. This is not our scheme, but this encounters some certain problems. Let's say you have initial message M. You first use the underlying secret sharing scheme to get these P messages, like M1 to MP are the P shares. And you can also consider and we have this tamper detecting codes, which is like a 3-split construction. So you can use to construct all 3 pairs of parties. For every triplet of parties, you use tamper detecting code to get 3 shares and accordingly give for the first party, you give this first register, second party, you give second register, and so on. You do that for every triplet of parties, and you give the shades accordingly. So you get, this is a candidate threshold tamper-detecting scheme. And naturally, you can also do, you first decode every triplet using the tamper-detecting code decoder. And if it detects, you abort. Otherwise, you get recovered shades, and then you reconstruct using the underlying secret sharing scheme to get M prime. Okay. So this natural thing that one can try, a compiler comes up with uh, this problem. I guess this natural one already gives certain security guarantees that we would want, basically. This candidate threshold secret sharing scheme is already gives you certain guarantee, which is weak property. Okay. So this, to argue such a thing, what we use is that our tamper detecting codes is 3 out of 3 secret sharing scheme. Not just that, it's also these two shades are always maximally mixed. And so basically, we can use for every triplet of parties, you can argue this, that either M0 prime, M1 prime, M2 prime, this is for triplet 0, 1, 2, that it's either abort or the 2. And you can use union bound for every triplet. For every triplet, I have this property. And you can use union bound to argue weak tamper detecting secret sharing. The only reason why we cannot get directly the strong tamper detecting secret sharing is because of the so-called abort, the selection bot attack. So what it means is that our tamper detecting codes cannot be composed in parallel. So in the sense that when you consider this triplet of parties, right, and you give shares, so basically one share of encoding of one share can be used to tamper with the second triplet. So that leads to the so-called this selective bot problem. This is not something that is unique to quantum setting. This is a problem that comes up when you design non-malleable secret sharing from non-malleable codes as well. So, and basically the issue is this, that whether each triangle decoding digit could be correlated with specific shades. And the solution is that our compiler basically uses the following things. The first is that we introduce something called triangle gadget. Basically, it's a variant of our 3-split tamper detecting codes with some nice properties. And additionally, we also need something called leakage resilience secret sharing scheme. We only using secret sharing scheme will not suffice, because we want to argue that any attack which adversary does to output abort, basically, like in one triplet, basically can be thought of as like, can be simulated as leakage on some subset of parties. So we want to reduce to such an attack. That's why we need this leakage resilience for the underlying secret sharing scheme. So basically, selective bot problem is exactly that encoding of one when you have two encodings, I cannot use encoding of one to tamper and correlate the probability of a bot. I mean, such a thing we get around by using leakage resilience, and on top of it, triangle gadget. And this is our final tamper detecting secret sharing scheme, that we, instead of tamper detecting code, we use triangle gadget, and the same one, rest is the same. And the decoder is again the same. You do first for every triplet the decoding and so on. The only reason that here we cannot give the threshold guarantee, we can give something called RAM, which is when T prime is like T plus 2. Like when you give the tamper detecting property, we need like T plus 2 parties, not just C party tampering does not suffice. The only reason is again because our gadget has certain problem. This is the gadget. The gadget has this problem. The gadget is a analog of tamper-detecting code in the following sense. Let's say if you are using the gadget on 3 registers for a triplet M0, M1, M2, then you basically use 3 times the tamper-detecting code, 1 time with lambda EPR pairs, another register with 2 lambda, and another register with 3 lambda pairs. And the reason why we do such a triangle gadget is that basically, if you look at how the triangle gadget encoding is happening, it's local. Like 3 parties, it's like triangle gadget encoding is local. It applies on MA separately, MB separately, and MC separately. And that lets us to basically overcoming the selective baud problem. Basically, tampering on one party's tamper-detecting code, we can also analyze as bounded entanglement attack. And under the bounded entanglement attack, we know how to argue tamper detection. So overall, basically this complicated construction, but the crucial idea lies in this triangle gadget and the way we use entanglement, staggered entanglement idea to reduce selective baud problem to bounded entanglement attack. Okay, and basically this is the staggered entanglement of triangle gadget argument. So basically our triangle gadget inherits nice properties of tamper detecting code that any 2 shares is maximally mixed. And also we get this share-wise tamper detection. For let's say once you for triplet 0, 1, 2, if you use the triangle gadget and you get prime candidate primes, then only the 2 parts of it are tamper detected. We don't know how to argue and for the 3rd part. That's the reason why we need T+2 instead of T, okay, for tamper detection. So overall, the new ideas that we give in this work is this staggered entanglement idea to reduce selective baud problem to leakage basically as a bounded entanglement attack, and then use leakage resilient secret sharing to solve the selective baud problem. This comes in non-malleable secret sharing as well. Like there were different ideas that people used for classical information, but we use the staggered entanglement idea along with leakage resilience to solve the selective baud problem. And this brings me to the 3rd result, which is basically connections to quantum encryption. That any T-split quantum tamper detecting code in local operations model must be single share encrypting. So in the classical setting, this is not true because people know how to construct T-split non-malleable codes, which are not single share encrypting. So this is the reason. This is a like departure again from classical codes, and the proof relies on quantum mechanical principle that suppose if you are given encryption of 2 states, ket A and ket B, and you could distinguish them. Like I could basically like if they are not single share encrypting, right? It means you can distinguish them. And if you meaning of single sharing, giving only 1 share out of T splits, you cannot tell the difference between 2 encryptions. Single share encrypting. I have plain text message M. I encode, I get T splits, right? Giving any 1 split, like 1, like let's say you take, let's say for the first split for 2 messages are the same, like encryption of 0 for the first split is indistinguishable from encryption of 1 for the first split. Then I will call that this is single share. And the thing is that if you could distinguish between 2 encoding of, like say, ket A and ket B, it also means that adversary can perform from transformation to modify an encryption of ket A plus ket B by root square root 2 to ket A minus ket B by square root 2. It means that some malleability sort of attack is happening, right? So that's why, because of this quantum mechanical principle, that we are able to show T-split tamper-detecting code must be single share encrypting. Otherwise, you can do this operation too. And those are the 3 set of results that we had. The Notably, the first is the three-split construction against bounded entanglement, and the second one is the application to tamper-detecting secret sharing scheme, and third one is connection to quantum encryption. And the open questions is that one of the open question that I am very much interested in is concentrate two-split non-malleable codes with entanglement. So this is open even for classical messages against quantum adversaries. And for tamper detecting codes, we only know how to do in the three-split model. Again, we don't know even with inverse polynomial rate in the two-split model. And we don't know how to construct tamper detecting secret sharing against more general adversary models like joint tamperings and so on. Yeah, that's all from me.